In part 1 of the protection introduction video, I listed the various issues that one should consider while contemplating high PV penetration. And we also looked at the ratings violation issue and the sympathetic tripping issue in more detail. And in this part 2 of the video, we will look at the loss of coordination issue and the reduced reclose sensitivity issue. Let's look at the fuse-to-fuse coordination first. The purpose of fuse-fuse coordination is to ensure that for a given fault, especially the persistent fault, the minimum possible number of customers are affected. This is achieved by having multiple fuses in series with their time current characteristics, or TCC. TCC stands for time current characteristics, well coordinated. So for example, in this figure, we have at least 2 fuses in series for any branch fault. Okay? So there is one fuse at the branch, and the second fuse is at the point where the lateral branches off from the main feeder. So for a fault at this location shown, fuse 2 should blow to clear the fault, whereas fuse 1 should not, so as to maintain the service to all the other branches without any interruption. Now this is ensured by the design shown in these TCC plots. Okay. So I have the time current curves of fuse 1 and fuse 2 superimposed on this plot. The x-axis corresponds to the magnitude of the fault current, and the y-axis is the time to clear in seconds. The coordination is ensured by having the TCC curve of the lateral fuse 1 shown here, to be always above the TCC of the branch fuse 2 shown here. So as an example, let's say the fault at this location results in a fault current of 100 amperes shown here. So note that it's the same 100 amperes fault current flowing through both fuse 1 and fuse 2. Okay? So if you look at the TCC of fuse 2 for 100 amperes fault current, it takes about roughly 0.2 seconds right here. Okay? 0.2 seconds to completely clear this fault, which is well below roughly 0.8 seconds or so for the fuse 1 to even begin to melt. Therefore, for this fault here, fuse 2 clears, fuse 1 does not operate, maintaining the continuity of service for the rest of the branches. Okay, so now when we add a PV system upstream of these 2 coordinated fuses, upstream is the keyword here for case 1. So obviously the PV system will contribute additional fault current, and this added fault current flows through both fuse 1 and fuse 2. So let's say the new total fault current with the PV included is about 130 amperes, as indicated by this red line. So once again, we can clearly see that for this new fault current, the fuse 2 clears much earlier than fuse 1. Okay? And therefore, fuse 2 clears first and fuse 1 does not, maintaining the coordination. So for case 1, where the PV is upstream of the fuses, the fuse coordination is not violated due to large-scale PV. We just need to ensure that the ratings of the 2 fuses are not exceeded because of the added PV fault current. In fact, the same conclusion is also true even if the PV is added at this point, downstream of fuse 1 but upstream of fuse 2. It's the same analysis. The case 2 corresponds to the PV generators added downstream of the fuses. For example, at this location, downstream of fuse 2. For the original fault, the fault 1 at this location, the fault current flowing through fuse 1 and fuse 2 are still the same, and therefore, as we saw in the previous slide, the fuse 2 is designed to blow first, maintaining the coordination. Okay. And once fuse 2 blows, the PV inverter should sense low voltage or the creation of an island and should shut off. Okay. So this for fault 1, this is not really a coordination issue. We just need to ensure that the inverter is able to sense this islanding condition and is able to switch off. Now, if we consider the fault at a slightly different location, say at this location indicated as fault 2, then for fault 2, the fuse 2 should not operate because the fault is not in this branch, whereas the fuse 1 now should operate to clear the fault 2. Now, corresponding to the fault 2, there will be fault current contribution from the PV inverter flowing in this direction through the fuse and flowing into the fault. Now, if this fault current is high enough, then it can exceed the TCC settings of fuse 2 and may blow the fuse 2 unnecessarily. So whether or not the fuse 2 clears for the fault 2 depends on the magnitude and the duration of the fault current from the PV. So one needs to ensure that the reverse current from the PV through the fuse does not exceed the TCC settings or the ratings of the fuse 2. And I should also mention that once the fuse 1 clears, then the inverter should sense islanded condition, and it should trip immediately. Now, in distribution systems, especially overhead distribution lines, a large number of faults or temporary faults or non-persistent faults. Now, these may be caused by the lines making contact with trees or due to flashover of insulators or animal birds contact. In a majority of these cases, long-term outages can be prevented by using automatic reclosers. The concept is that when a fault occurs, the recloser will open instantly based on its instantaneous or fast curve setting. If the fault is really temporary, then it disappears by itself and any arc is extinguished during this de-energized period when the recloser is open. The recloser then closes after a delay, and if the fault has cleared, it remains on, but if the fault is not cleared, then the recloser goes through one or two more reclosing attempts and then finally locks out. Now, for reliable operation of the recloser, it needs to be properly coordinated with its downstream fuses. Now, corresponding to this simple one-line diagram with just one recloser and one fuse, here is a simplistic coordination scheme where the two TCC curves of the recloser, the instantaneous or the fast curve of the recloser shown in green, and the slow curve of the recloser shown in blue. Now, these two TCC curves are superimposed with the TCC curve in red of the fuse. Now, any operating point inside this yellow box represents the region of coordination. Okay. So let's assume that the recloser is programmed for two instantaneous trip attempts, and then a third attempt using the slow curve, and then finally lockout. Okay. So as an example, let's consider this to be the fault current. So clearly the recloser opens first because the instantaneous curve setting is well below that of the fuse for this particular current. Okay. So if the fault clears itself, then during the second fast attempt, the recloser closes and remains on. But if the fault is still not cleared, then the recloser opens again because it is still operating at its instantaneous trip setting, and therefore it is faster than the fuse clearing time. If the fault is still persistent, then the fuse clears this time because the fuse clearing time is well below that of the recloser time under the slow curve setting. Therefore, the fuse 2 clears, and and when the recloser closes again, it does not see the fault because the fuse has cleared the fault, and therefore it remains on. Now, if for some reason the fuse fails to clear the fault, then the recloser will again close into a fault, and then it would eventually lock out, providing backup protection to the fuse. Okay. So this way, the so-called fuse saving strategy ensures that for temporary faults, the fuses do not blow, and more importantly, there is no long-term outage to the branch which has the temporary fault. However, this is at the expense of momentary power outages or disturbances for all the customers downstream of the recloser, which can be a significant drawback. So how does the large-scale PV affect the recloser fuse coordination? To study this, we add the PV generator here, which is upstream of the fuse and downstream of the recloser. And here are the original TCC plots of the recloser and the fuse that we discussed in the last slide. Now, as the PV is added, there are two ways in which the coordination can be affected. First, from the circuit, we can see that the current through the fuse, the fault current, increases because of the additional PV fault current. So it may push the operating point beyond this yellow box where there is no coordination. Okay. But more importantly, the current through the recloser and the fuse are not the same in this case. I fuse is I recloser plus the PV current. So the fuse current is larger by an amount equal to the PV current, noting that these are complex phasor additions. Okay. So because of that, if you look at this operating condition, the fuse sees a larger current versus the recloser sees a lower current. Therefore, even with instantaneous or the fast curve setting, the recloser takes a longer time to open. So therefore, the fuse is the first one to clear. So this way, we lose the recloser fuse coordination if we are following the fuse saving strategy, and this results in unnecessary loss of the fuses and more importantly, unnecessary long-term outages for the branch with the fault. So the main conclusion is that if you are adopting the fuse saving strategy, then the recloser fuse coordination needs to be carefully studied under high PV penetration. The same conclusion also applies to the substation relay, the relay to fuse coordination upstream of the reclosers. We saw that the fuse saving strategy results in momentary outages to a very large number of customers for temporary faults. So to avoid this, some utilities use what is known as the fuse clearing strategy, where the recloser is always set to its slow curve setting, and the fuse clears first for all the faults, regardless of whether they are temporary or persistent. Here are the TCC curves under the fuse clearing strategy. Clearly, the recloser has just one setting, the slow curve setting, and it is by design always above the TCC of the fuse curve so that the fuse clears first for all the faults. Now, the addition of the large PV system only improves the situation under the fuse clearing strategy, because the extra fault current through the fuse relative to the recloser only makes the fuse to clear even faster because the fuse sees a higher current. And this is the intention in the fuse clearing strategy, that the fuse blows first. So the conclusion is that if you're following the fuse clearing strategy, then there is no need for a separate investigation of the recloser fuse coordination under the high PV scenario, because the PV is only improving the situation. We just need to ensure that the ratings of the fuses and the reclosers are not violated. Okay, so the final topic that we will see in this video is the the reduced relay and recloser sensitivity for remote faults because of PV. When a PV system is placed downstream of a recloser, the fault current seen by the recloser for a remote fault actually decreases, and therefore the reach of the recloser reduced. Now, this may at first sound counterintuitive, but this can be easily explained with this simple example. In this circuit, we for a given fault at this location, the fault current that flows from the substation and through the recloser can be easily calculated. The substation is modeled by its Thevenin's equivalent voltage and the Thevenin impedance, the Z sub. Then the fault current through the recloser, I recloser without the PV, is simply E divided by all of these impedances, Z sub plus Z1 plus Z2. Okay, simple Ohm's law. Now consider that the PV generator is added downstream of the recloser, and this PV can be modeled as a current source IPV, and IPV is a phasor. There is a complex number with a magnitude equal to the inverter maximum fault current value and an angle relative to the substation voltage E. Now, since we have two sources, one is the substation voltage source and the other is the IPV current source, we can use superposition to calculate the new recloser current. So that is we consider each source separately and add their independent current contributions at the recloser. So when we consider E, the substation voltage source, the current source is opened. So that component of the recloser current is exactly same as what we calculated before, E over all of these impedances, because that's what we calculated without the PV. Okay. So that is the first component. For the second component, we consider the IPV. So when we consider IPV, this voltage source, this is shorted. Okay, so this is shorted, and we still have the Z sub. Okay, that's a Z sub. Okay, so the current from IPV splits into two parallel paths. One is this path, and the other is this path, which is what we are interested in, the current through the recloser. Okay, so this current using current division is same as IPV times the impedance of the opposite path, that is Z2, divided by all the sum of all the impedances. Okay, so that is this term. The negative sign is because the current is calculated going in this direction, which is the opposite direction compared to the current from the substation. So clearly the IPV, the PV generator fault current, reduces the fault current seen by the recloser by this amount. Okay. Keep in mind that the currents and voltages, they are all in complex phases, and Z1, Z2, etc., they are all complex impedances. And a similar calculation can show that the fault current seen by the substation relay also reduces because of the PV system downstream, and therefore the sensitivity of the substation relay also for remote fault is reduced. When a recloser is selected and its settings are determined, it is done such that the recloser's pickup current is less than the minimum fault current due to fault at any of the remote ends in its zone of protection. Okay? So it may be the fault at this blue circle or somewhere at this remote end of this branch. Okay? So now when the PV generator is added, we know that the fault current seen by the recloser reduces by this amount. So with this new case, the fault at this blue circle may not generate enough fault current as seen by the recloser to exceed its pickup current setting. Okay? So it may be more like a fault at this red circle or lower that will cause the recloser current to exceed its pickup current setting. Okay. So that means the zone of protection for the recloser has reduced from this original larger blue area to the smaller area shown. Now, if there is a sufficient margin between the existing pickup current setting and the expected maximum load current, now considering all the maximum inrush currents and so on, then a simple solution for this high penetration case would be to change the recloser settings. Now, that may not be possible in all the cases, meaning there is not sufficient margin. Then, if that is not possible, then we may need additional reclosers to provide protection for the zone that are not protected by these reclosers. That is, all the area outside of this new zone of protection. To protect that, we may need a recloser somewhere in this region. Okay, now a few more points about the sensitivity reduction for the relay and the reclosers. Now, from this equation for the recloser current, we see that the reduction seen by the recloser in its fault current depends on three parameters. First is the IPV magnitude, second is the IPV phase angle, and the third is Z2, which is in some way a measure of the proximity of the PV system to the recloser. The closer they are, higher is the value of Z2 for a given fault location. So the PV fault current magnitude, higher this value, always lower the sensitivity of the recloser. In terms of the phase angle of the fault current from the inverter, which is a strong function of how the inverter control circuit is designed. Now, the worst case is when the inverter fault current phase angle matches the phase angle of the fault current from the substation. Okay. Then these are in phase and the reduction is much larger. Therefore, the sensitivity is lower. And the third point, the proximity of the PV to the recloser. The closer the PV is to the recloser, higher the Z2, and therefore larger is the reduction in the fault current seen by the recloser, or lower the sensitivity. Now, this is an important observation because unlike in many of the other PV related impacts, such as voltage violations or power quality issues, where farther the PV system from the substation or the recloser, higher the impact. Okay? But here, in terms of the sensitivity reduction, it is just the opposite. That is, closer the PV is to the substation or the recloser, higher the impact in terms of the reach of the relay or the recloser. Okay, so that completes this video. In the next few videos, we will discuss some of the methods and tools to quantitatively analyze the various impacts of PV on protection device coordination using the detailed feeder model developed earlier.